In the first point, there are total 6 points in electrostatics of a conductor. Definitely one will come in exam. The first point is inside a conductor. It is one marker question. Electric field is 0. Means inside the charges lie on the surface area. Inside the conductor, there is no charge. No charge, no electric field. This is the first point. Second point, at the surface of a charged conductor, electric field is normal to the surface. Example, think that the electric field is not normal to the surface. It is not normal to the surface. It goes like this. Example, it's not normal to the surface. If it is not normal to the surface, what will happen? Suppose what will happen? This electric field will exert a force on this charge, and the charge will move from one place to another place. Is that clear? Once again, if the electric field is not normal to the surface, so when it is not normal to the surface, it exerts a force on the charge, and the charge will move from one point to another point. Okay, that means there is some displacement in the charge. So, but in static situation, there is no movement. In static situation, there is no movement of the charge. Charge will not move from one place to another place. So this is where it failed. That means our contradiction is wrong. That means what? Every time the electric field is normal to the surface. Is that clear? Our contradiction is wrong. But what was our contradiction? We thought like electric field is not normal to the surface. So our contradiction is wrong. Therefore, electric field is perpendicular to the surface. Clear? Third point. The third point is the interior of a conductor can have no excess charge. Third point. The interior of a conductor can have no excess charge. Yeah, bolo. So can have no excess charge in the static situation. Okay, in the static situation. Okay, the interior of a conductor can have no excess charge. Like suppose now, example, this is a body. We are adding the charges. See, first lap, second lap, third lap, like fourth lap. We are keeping on adding the charges now. If you keep on adding the charges, it will reside on the surface only. It doesn't mean that if you give extra charges, it doesn't go inside the body. What will happen is the extra charges will be still on the surface. If it is not able to cope up, there will be a spark, but it won't go inside the body. Understood? So once again, see, if you keep on adding the charges on the body, it goes on the surface of the body. It doesn't go inside the body. So the interior of a conductor can have no excess charge in the static situation. This is the third point. Fourth point, electrostatic potential is constant throughout the volume of the conductor. Electrostatic potential is constant throughout the volume of the conductor. At the conductor, throughout the volume of the conductor, and has the same value on its surface. And has the same value on the surface. Means what? Suppose there are two graphs. What is the first one? Is electric field versus distance graph, and the second one is what? Electric potential versus distance graph. Now what happens here? If you see this carefully, electric field is constant here and it decreases like this. But if you look at the potential graph, it is constant and comes down. Is that clear? It's constant and it comes down. Is it clear? So this is about the electric field and this is the potential. Electric field versus distance graph and potential versus distance graph. Is that clear? This is about the fourth point. This graph can come in exam. Is it clear of you?
Yes, sir.
Yeah, okay. Then two more points. We will discuss that. Then we are done with it and we can go with dielectrics and polarization. Electric field is the surface of a charged conductor. So what is the formula here? E is equal to what? E is equal to sigma by epsilon 0. Okay. So here we already know this one, right? So on the surface of a, suppose there is a sheet, like there is a sheet here. Now there is a sheet like this, and the charges are residing on the sheet, and electric field is coming out. What is the formula here? We have sigma is equal to Q by epsilon 0, and Q is sigma is equal to Q. Sorry, flux phi is equal to Q by epsilon 0, and the second formula is phi is equal to E dot S. Phi is equal to E dot S. Okay, so what is the formula here? E dot S is equal to what? E dot S is equal to Q by epsilon 0, implies E is equal to Q by S into epsilon 0, implies E is equal to sigma by epsilon 0. This is the formula what he got. The sixth one is what? Electrostatic shielding. Sixth one is electrostatic shielding. Did you understand this one, all of you? Is it clear, all of you? This one. Next is electrostatic.
Could you explain that once more?
Now suppose there is a sheet, electric field is coming out of that, and E is equal to what? Sigma by epsilon 0. We have, sorry, just to leave this one. So we have Q is, this is from Gauss law, and this is from the electric flux formula. You put both of them, you get this. Then what is Q by epsilon 0? It is sigma by epsilon 0. Next is electrostatic shielding. Electrostatic field inside the cavity is 0. So field inside the cavity is 0. Field inside the cavity is 0. Means what? Suppose suppose there is electrostatic, like there is a surface like this. Okay, there is a surface like this. So what happens here? It's like a blood cell, RBC, something like that. So when you place this in the electric field, all positive will be here, aligned in this way. All negative will come in this way. And here charge is equal to 0. When charge is equal to 0, electric field is also equal to 0. When charge is equal to 0, electric field is also 0. But potential remains constant. V is equal to V0. Potential remains constant inside the cavity. Is that clear? Potential remains constant inside the
Yes,
cavity.
sir.
Equal to V0. Clear? So Q is equal to 0, E is equal to 0, then V is equal to V0. So what happens? This particular concept is used where in cars, in designing of the cars. When you sit in the car, you are like sitting in the cavity actually. The tires are insulators. Tires are insulator. When you are moving on the road, you are inside the car. The whole body is metal. What happens? The whole body will get charged when you move at a speed. Understood? So what happens is the whole body is like, sometimes you go out of the car and just touch the body, will get a shock because charges are developed on the surface of the car. Clear? So we are like sitting in the cavity. So do we feel the charge? No. Inside it is completely insulated. The metal body is inside it completely insulated, like the car seats and the plastic or the fiber body is there inside internally. Okay. So what happens? You are not touching the metal car from inside. So you are safe. Okay. And this is one case. Second example, when the aeroplane is moving in the air, flying in the air, then so many charges are developed on the surface of the body. So what happens? You are completely insulated inside. You are not feeling the charges. But once you land it, what happens? When the wheel touches when the plane wheels or the tires touches the runway, you can see the sparks. Did you notice any time this one? Why? Because in the old ones you don't see anything. In for small ones you don't feel, because once it lands on the runway, we touch the what these people do is, when the ground stop, they bring a metal rod and touch the plane to the runway. All the charges which are residing on the surface will go to the ground. But in the latest designing of the aeroplanes, what they have done is, in the tire car itself, in the tire also, they made one metal strips like this. And there is a metal brush touching the body like this constantly. So what happens? Whatever the charges are residing on the plane, that is body of the aeroplane, all the charges will go to the tire, and the point it touches the ground, all the charges on the aeroplane will go to the ground because of the metal strips. So that is why there is a spark. There is a metal strips inside the tire.
The tires don't get.
No. Generally, the aeroplane tire has a life, maybe only 10 landings, 15 landings. That's it. not more than that. You know this one?
Brakes also.
Yeah, that's what they have to remove these tires and brakes. They have to change. So that is why landing and takeoff is very, very important for the aeroplane. They don't multiply unless and until it's required, then only they land it. Okay, all this is like expense also, because maybe one aeroplane can land and 20 times, or after that they have to change the tires and brakes and all this concept is there. So this is about the electrostatic shielding. Okay, note down this one. Is it clear, all of you?
I want to comment something, but I'm not.
Next we have dielectrics and polarization. Okay, so dielectrics and polarization. So the last topic of this first part, the potential part. Okay, so we have non-polar and polar molecules. What do you mean by non-polar molecules? This is chemistry based. Can you tell me? Non-polar molecules. Can anyone say what is non-polar molecules? Yeah. Chemistry. Huh?
Zero.
Wait. Now, center of mass of positive charge will coincide with the center of mass of negative charge. Okay, means if the center of mass of positive and negative overlaps, then there is no dipole moment. Example, like hydrogen is there, single bond, triple bond, oxygen is double bond. Okay, diatomic molecules, diatomic homodiatomic, not hetero, homodiatomic molecules. Sorry. So suppose if you are placing these molecules in the electric field, what happens? There is no dipole moment. There is no dipole moment. Okay, means they don't rotate in the direction of the electric field. Is that clear? When you place this type of molecules in the electric, in this one, there is no dipole moment. Okay, so there is no dipole moment. There is no dipole moment. Okay, so next one is what? The next is polar molecules. Is it clear, all of you? Polar molecules. In polar.
Yes, sir.
In polar molecules. In polar molecules, what will happen if the center of mass of positive will not coincide with center of mass of negative? So what will happen? Like example, HCl is there. HCl, this is plus and this is minus. Already we know. So what happens when you place this type of molecules in the electric field? What happens? H plus will be in the direction of the field and Cl minus will be against the direction of the field. Against the direction of the field. Okay. So next is what? Dipole moment per unit volume is called polarization. Dipole moment per unit volume. Dipole moment per unit volume is polarization. Dipole moment per unit volume is said to be polarization. Okay, denoted by P. How much dipole moment is taking place? Means when you place it in the a dipole in the electric field. So how much rotation or how much it will flip in the direction of the electric field? That is said to be dipole moment per unit volume, which is known as polarization. So P is equal to, like, some simple example I will give. Like suppose a speaker comes to your place and to your school or something, he gives some, what we say, life lessons, or maybe some encouragement, motivational speeches. So what happens? Some people now they become really motivated. Some fellows, they don't bother it, but some people really they get motivated. Means when the speaker came, how many people were motivated? That is a typical polarization. He polarized. The same thing happens with the political party leaders also. They come to your place and they give a speech, very revolutionary speech, and then they change the minds of the people. That is called polarization. So dipole moment, and when you place a dipole in the electric field, how much dipole moment takes place? That is said to be polarization. Okay, so we have P is equal to chi E into capital E. P is equal to what? Chi E into capital E. Chi E is said to be what? Chi E is said to be electric susceptibility. Electric susceptibility. Chi E is said to be the electric susceptibility. And E is the electric field. Clear? So this completes your first part. So tomorrow only one class I can finish off the capacitance. Parallel plate capacitor, series, parallel, energy stored in the capacitor. Derivation is not there for energy stored in the capacitor. Only qualitative explanation is there. So tomorrow I will finish off the theory part, and after that we can go for current electricity. Clear, all of you?
Yes, sir.
Okay. So thank you so much.